between two vectors, how to find projection, and how to find work. So I'm going to kind of quickly go through each 4 of these, and then there is a note sheet for you to have some practice problems, and the answers will be posted to those as well. But this video is just going to quickly go through how to do all 4 of these. So the first thing is the dot product. So basically you have 2 vectors and we're asking you to dot them. So the biggest thing I want to point out is the notation. If you'll notice, it'll look like this, u dot v. That's not u times v. This is vector's way of multiplying, okay? So that means the dot product. And so how you do that is it's actually rather simple. You just take the 2 I components or the 2 horizontal components, multiply them together. You take your 2 j components, which is the vertical components, multiply them together, and you add them together to get one number. So the result is what we call a scalar. It doesn't really have any meaning behind it, but the dot product is used in many mathematical formulas, which you'll see in a second. So it's just kind of like a skill that we need to teach you how to do. It doesn't necessarily have meaning on its own. But the key is it's not a vector at the end. You add them together to get one single scalar number. Okay, so consider 2 vectors, a u and a v. And if we say u dot v, we literally want you to just multiply them. And so you would get 2 times -3 plus -1 times 4, and you would end up with -10. And that's it. And again, it has no relevance. It's just, can you find the dot product? So one of the things the dot product is useful for is actually in the formula for finding the angle between 2 vectors. Okay, so the formula for the angle between 2 vectors is, you're going to take the cosine of theta is equal to u dot v over the magnitude of u and the magnitude of v. So remember, these double bars mean magnitude. Okay, and we're going to find the angle between them. All right, so we're going to use that, and we're going to use their 2 vectors u and v again. So if I want you to think about it, I actually drew these vectors for you. So 2, -1 is actually this vector here, and v, -3, 4 is this vector here, and I wanted to find the angle between them. So you can see it's a relatively large angle, but we can find it. So the first thing is we got to find u dot v. Now, conveniently, we already did that on the last screen, which we got -10. And then at the bottom, we want to find the magnitude of u and the magnitude of v. So remember, to do that, it's basically a squared plus b squared equals c squared. So 4 squared plus 1 squared, -1 squared, square rooted, and -3 squared and 4 squared, square rooted. So I got this. This is a 3, 4, 5 triangle, and this is the square root of 5. Okay? Now, this whole chapter is calculator, so you will need your calculator for this, and you will want to be in degrees, not radians. And so, oh, for a second I was, why is there 2? We had -6 plus -4 is -10, and then we divided by 5 to get -2. But it doesn't really matter, because at the end of the day, you need to figure out the angle. And so you're actually going to do inverse cosine, and we get 153.434. Because it's a calculator section, you do want to do 3 decimal places. And you can see our answer makes total sense, because this clearly looks like it would be 153 degrees. Okay, so this is how you find the angle between any 2 vectors. You find the dot product and divide by its magnitude, and then do inverse cosine. So why do you think we use inverse cosine instead of sine or tangent? That's a good question. And I hope you're thinking principal solution. It always comes back in every chapter. Cosine is actually the only one that will give us angles between 0 and 180. And so if you think about it, that would cover all the vectors, the angles between 2 vectors. Sine and tangent aren't going to do that, and they abide by their principal solution when you use the calculator. It also, the formula for the proof for the angle between 2 vectors actually comes from the law of cosines. So if you're interested in that, that's something that you could look up. Okay, so a little insight. If you actually know what the dot product is, you actually have an idea of what type of angle you have without having to draw it out. Okay, so if you think about this formula, if I did u dot v, and I ended up with 0, that would mean the top would be 0. So the magnitude or the length of u and v are irrelevant, because you have 0. And if you do the inverse of cosine, what angle gives you the cosine of 0? It's actually 90. So if you end up with a dot product where the answer was 0, that actually means they're perpendicular. But in vector world, we actually don't use the word perpendicular. We use the word orthogonal. So perpendicular, orthogonal, and normal are all terms that mean meet at a right angle. Perpendicular is common to see in our normal function world. Orthogonal is what we use in vectors. And then normal is when we have a plane and a vector. So we'll get to that in a couple units. But for now, when we say u and v are perpendicular, we're actually saying they're orthogonal. Okay, so then if u dot v actually has to be a bigger number than 0, you would have a positive number divided by their lengths, which would be positive. So when you do that, when you do the inverse cosine of that, you're going to have all the positive answers, which actually means you're going to have an acute angle, versus if u dot v was negative, their magnitudes are always going to be positive. So you have a negative, and so that puts you in quadrant 2, and the inverse of cosine in quadrant 2 is actually an obtuse angle. So just a little insight into like behind the angles. All right, let's talk about projection, the third topic. This one gets a little bit more tricky. Okay, so we're going to talk about projection of vector A onto a vector B. And it's notated like this: projection A is the big one onto B. And basically what that means is you're trying to find out how much of vector A is in the same direction as vector B. So it's determined by dropping down a perpendicular down from the tip A, and we're trying to figure out how much of A was actually going in the same direction as B, if that makes any sense. So the formula for finding it is actually this: projecting A onto B is we're going to dot A and B together. But then we're going to divide it by the magnitude of B squared, and then we're going to multiply it by B. So when you're finding a projection, unlike doing an angle and the dot product, you're actually ending up with a vector. Okay, so your answer should be in vector form because you're essentially creating this green vector here, and that's telling you how much of this A was actually going the same direction as B. Okay, so let's use this formula with two different vectors. So I have this vector u, which is 6, 2, and I have this vector 5, negative 5. Okay, and I'm going to go over to Desmos really quick just to show you what's going on. Okay, so I have this vector here. This is the vector 6, 2, and this is the vector, what was it, negative 5 or 5, negative 5, going this way. So I want to know how much of A is projected onto B. Okay, so to do that, let's do some little math. First, I'm going to do A dot B, which should be easy. 6 times 5, 30, plus 2 times negative 5, okay, which is 20. I think I'm going to go this way. Okay, and then I'm going to divide it by the magnitude of V squared. So 5 squared plus 5 squared square rooted. So really you just don't need the square root part. So it's 50. So 20 over 50. And then I multiply that by vector B. Okay, so really what you're doing is you're actually like scaling B back to only be what is in terms of A. So A dot B divided by this magnitude is going to end up with a scalar, and that scalar number is going to get multiplied by this vector. So I'm taking vector B and I'm kind of scaling it back to see how much of A is on B. Okay, so if I do that, 20 divided by 5 is actually 2/5, right? Times that. So I end up with this new vector. So if I wanted to just find the projection of U onto V, it would be this new vector of 2, negative 2. So let's go back to Desmos real quick, and I'll show you what that means. So this new thing I'm putting up is this is our new vector 2, negative 2. And if you think about it, here's that perpendicular line. Boom. So this is A, and this vector here of 2, negative 2 is how much of A was actually going in the same direction as B. So you're kind of dropping this perpendicular down to get this other vector. Okay, so if you're just trying to find projection, you're done. The answer was 2, -2. But then what you can do is you can also rewrite it in terms of, if I wanted to write this vector here, it's basically saying I'm going to take this projection vector plus the perpendicular vector, and that would have ended me in the same spot as this original vector u. Again, so like this projection vector plus the perpendicular vector would allow me to get this original vector, because tip to tail, I'd go here, then I'd go up here, and so the resultant would just be vector u. So basically what we need to find is we need to find this perpendicular vector. So I can kind of set up an equation and I can work backwards. So my projection plus the perpendicular has to equal 6, 2. So I can figure out what would that be. So if the projection was 2, that means the perpendicular had to be 4 to end up with 6. And if this was -2, this would have to be 4 to end up with 2. And so this is the projection vector. This is the perpendicular vector. These two have to add up to get to the original. And that's what it means by write u as the sum of your two orthogonal vectors, basically the projection vector and the perpendicular vector. All right, last one, work. Now, some of you might be familiar with work because you're in physics. So the work that we do is much simpler. You'll see that we actually have like a somewhat of a different formula, but it's just simplifying it in a sense. And so we want to know how much work is going to be done if I push an object from one point to the other. So that depends on a couple of things. Number one, basically, how far am I going to push it? So the distance from A to B. And number two, how heavy is it? So the work that I'm going to exert is how heavy is something in any direction, and then what distance am I going to push that thing? Am I pushing it a block or am I pushing it a mile? That's really going to be a different amount of work. So I'm going to take my force vector and I'm going to dot it with my position vector. So I'm dotting two vectors together, so the answer is a scalar. Okay. So basically, when you guys are doing these in physics, you do a lot of things that are up a ramp or other things like that. We're going to keep it much simpler in the math world. We are pushing a lot of things along the horizontal, okay, which makes it much easier. So if I want to pull a wagon and I'm going to have, I don't know, let's say my child in the wagon who's 20 pounds. I'm going to pull the wagon at an angle of 60 degrees with the horizontal. And I want to pull this wagon 50 feet. I have to find the work that's going to happen. So first thing is I'm going to find my force vector. So the force goes in front and your angle, so 20 times the cosine of 60i plus sine of 60j. This is a calculator question, so you could figure it out. Although 60 degrees is something I know. So the cosine of 60 is a half, the sine of 60 is √3/2, and distribute the 20. I ended up with a force vector of 10 and 10√3. Okay, if you're using your calculator, don't round until the very end. Position vector. So it didn't specify. It said I was just going to move it 50 feet. So we're just going to assume it's from the origin to make our lives easy. So I'm moving from one point to the other. So then if I figure out a position vector, I technically subtract. So 50 minus 0 is 50. 0 minus 0 is 0. And so this vector represents I'm moving 50 feet only in the horizontal direction. And I'm just going to assume that it's the positive direction. Okay. So if I want to find the work, what I'm going to do is I'm going to dot those two things together. So I end up with 10 times 50 plus 10√3 times 0. So that drops out. So basically 500. And whenever you're doing work, the common unit for it is foot-pounds or Newton meters. Most of what we do in math is actually the foot-pounds because we always have everything in foot-pounds. But if you're doing this in physics, you will see newtons and meters, which is actually joules. So again, you're going to end up with a scalar, not a vector at the end. You're dotting two vectors together to get a scalar. And that's basically how you find all four of those things. I know that's a lot. But here are the formulas again. This is something that you need to know. Again, the dot product is going to give you one answer, a scalar. The angle is going to give you an angle. Make sure it's in degrees. Projection, this is the only one that's actually going to give you another vector, and work is going to give you a scalar. So it's time for you to practice all 4 of these things. So good luck.